Hello, in 7.6 we're going to review L'Hopital's rule when evaluating limits. Now remember, we have some limits that have an indeterminate form. Okay? So if we look at 0, 0 or infinity over infinity, that means it's indeterminate. We cannot determine the limit. We need to do something else. Luckily, if you do get 0 over 0 or infinity over infinity, you can use L'Hopital's. The remaining limits are also indeterminate. However, you cannot use L'Hopital with those forms because they're not fractions with 0 over 0 or infinity over infinity. So recall what L'Hopital's rule says. It says that if you get a 0 over 0, you're allowed to reevaluate your limit by taking the derivative of the top function over the derivative of the bottom function. So let's look at example 1. When I plug in 0 for my x value, I'm going to get, let's see, e to the 0 is just 1. And then 0 minus 1, so I get 0 over, if I put in 0 for x in the denominator, I get 0. So again, that's an indeterminate form. It doesn't mean the limit does not exist. It doesn't mean the limit is 0. It means we have to do something more. So the something more that I'm going to do is I'm going to use L'Hopital's rule. So this is just my notation to say that I am using L'Hopital's rule. So I'm going to use L'Hopital's rule to take the derivative of the top and the bottom. So remember, the limit is still there. We haven't evaluated the limit yet. Sorry, this is a terrible x. So the derivative of e to the 3x is just 3 e to the 3x minus 3. And in the denominator, I get 2x minus 5. So notice when I reevaluate this limit, it's going to be 0 over negative 5. And that is 0. Okay, so the other form of L'Hopital's is infinity over infinity. And now remember, it could be negative infinity over infinity as well. And it would still satisfy L'Hopital's rule. So again, if you get infinity over infinity, you're allowed to take the derivative of the top and the bottom separately and reevaluate your limit. So let's look at example 2. Example 2, as x goes to infinity, this becomes infinity over infinity, which is an indeterminate form. However, I can use L'Hopital's. So this would be equal to the limit as x goes to infinity. Derivative on the top is just 4. The derivative on the bottom is 1 over x. In other words, this is equal to the limit as x goes to infinity of 4x. Okay. And then putting in infinity for x, we just have infinity. Okay. And we're done. So let's move on to the next page. Let's go ahead and evaluate. Okay, let's go ahead and, oops, got the wrong example up there. Let's go ahead and evaluate other indeterminate forms. So if we have a form such as 0 times infinity or negative infinity and infinity minus infinity, again, that's indeterminate. We need to do something more to evaluate the limit. So what we're going to try to do is change it to a quotient or a fraction and then use L'Hopital's. Okay. So example 3, if we put in 0 for x, sine of 0 is 0. Natural log of 0 is undefined, but remember, we're coming in from the right-hand side of 0. So as we approach 0 from the right, natural log is negative infinity. Okay. So again, this is an indeterminate form. What I'm going to try to do is create a fraction. So this is equal to the limit as x goes to 0 from the right of natural log of x. I'm going to put the sign of x in the denominator and create a fraction. And now this is just going to be cosecant in the denominator. So the limit as x goes to 0 from the right of the natural log of x over cosecant of x. Reevaluating the limit, I have negative infinity over infinity. Okay, so as we approach 0 from the right, cosecant has an asymptote and approaches positive infinity. So I am going to now use L'Hopital's rule and take the derivative on the top and the bottom to get the limit as x goes to 0 from the right of 1 over x. The derivative of cosecant is negative cosecant cotangent. Okay, so that's going to be equal to the limit as x goes to 0 from the right of 1 over, I'll just bring the negative out in front, x times cosecant of x cotangent of x. And I did want to play around with this a little bit to remind you of a special limit that we had from Calc 1. Notice that this is the limit as x goes to 0 of negative 1 over x times 1 over cosecant is going to be sine times 1 over cotangent is just tangent. Okay. So I'm going to bring these two together and see if you recall what this special limit is. Now I'm going to ignore this negative. I'm looking at sine of x over x as x goes to 0. And then times tangent. So this was that special limit, and that's equal to 1, but I have this negative in front of it. And the limit as x goes to 0 of tangent is 0. So this limit is negative 1 times 0, which is just 0. So let's look at another example. If I had to evaluate the following limit as x goes to 0, again from the right, of 1 over sine of x minus 1 over x, that turns out to be infinity over infinity. Or I'm sorry, infinity minus infinity. So I can't use L'Hopital's. I do want to create a fraction, so it just seems natural for me to take these two fractions and combine them with subtraction. If I do that, I have the limit as x goes to 0 from the right of x minus sine of x over x times sine of x. Okay. So when we evaluate this expression, I do get 0 over 0. And I can go ahead and use L'Hopital's rule and take the limit as x goes to 0 from the right of 1 minus cosine of x over, and then just be careful because we have a product of functions of x in the denominator. So we need to use the product rule, which would be derivative of x, which is 1, the sine of x stays the same, plus x times derivative of sine is cosine. Now when I reevaluate this limit as x goes to 0, I have 0 over 0, which is still indeterminate. So I'm going to use L'Hopital's again. Okay. You could try playing around using some trig identities, but I think this would be faster. In the denominator, this is going to be just sine. or the numerator, sorry, I apologize. But the denominator is a little bit more complicated. The derivative of sine of x is cosine of x plus, and then I have to use the product rule on x times cosine of x. So that's going to be cosine of x plus x times negative sine of x. Okay. So when we evaluate this, I get 0 over 1 plus 1 minus 0. Which is just 0 over 2. So the limit is 0. We still have to substitute this in. Move on to the next page. We're going to look at other types of indeterminate forms. So something that you should notice with these forms, 1 to the infinity, we have base 1, exponent infinity. 0 to the 0, we have a base of 0 and an exponent of 0. Infinity to the 0, we have a base and an exponent. So these are all functions of x where you have a base and an exponent. Okay, so if we do have the limit of a function with an exponent of also of a function of x, and when we evaluate the limits we get one of these three indeterminate forms, then we can evaluate the limit by first, number 1, evaluating the limit as x goes to a of g of x the exponent times the natural log of f of x. Okay, and we're going to call this L. Once we figure out what that limit is, then the limit of our function is actually going to be e to the L. The question becomes, why? Well, this goes back to properties of exponential function e to the x and the natural log. So let's say we have some function of x and the exponent is also a function of x. We are allowed to take e to the ln of our function with its exponent. Okay, those are equal. What that allows us to do is to take the exponent g of x out in front of the natural log. So this is e to the g of x times the natural log of f of x. So if I were to take the limit as x goes to some value a of f of x to the g of x, it's going to be equal to the limit as x goes to a of e to the g of x natural log of f of x. And then we are allowed, because the exponential function is continuous, we are allowed to take the limit up into the exponent. So this is e to the limit as x goes to a of g of x times the natural log of f of x. So when you look at the procedure for evaluating limits of this form, you would first evaluate this limit as x goes to a of g of x times the natural log of f of x. And that becomes the exponent on the base e. So sometimes it's nice just to know why they have these procedures. It's easier to remember. So let's look at an example. Let's say we have the limit as x goes to 0 of x to the x. So we have base x, exponent x. If I evaluate this limit, I get 0 to the 0 power, which is an indeterminate form. So I'm going to use that procedure where I'm going to first figure out the limit as x goes to 0 of x times the natural log of x, right? Its exponent, natural log of base. Now this is indeterminate. It's 0 times negative infinity. So what I'm going to do is try to create a fraction as I did before and use L'Hopital's. So this is equal to the limit as x goes to 0 from the right. I'm going to keep the natural log in the top and drop the 1 over x in the denominator because that's actually easier for me to differentiate. And now when I reevaluate this limit, I get negative infinity over infinity. So sorry about that telephone ringing. Let's go ahead and use L'Hopital's to evaluate this limit as x goes to 0 from the right. So when I compute the derivative, it's 1 over x divided by negative 1 over x squared. So simplifying, we get the limit as x goes to 0 of negative 1, or I'm sorry, of negative x. So as x goes to 0, this is just 0, but remember we're not done. So that would be our step 2. And we get the limit as x goes to 0 from the right of x to the x is equal to e to the 0, which is equal to 1. So again, we have to substitute that limit back into the exponent on e. Let's go to the other page, the next page, and look at another example. Okay, so in example 6 we have to evaluate the limit as x goes to infinity of 1 plus 1 over x to the power of x. So as x goes to infinity, this just becomes 1 to the infinity power, which is an indeterminate form. So I'm going to first evaluate the limit as x goes to infinity of exponent times natural log of the base. And if we put in infinity, this becomes infinity times 0, which is an indeterminate form. I'm going to create a fraction by dropping the x down into the denominator to get the limit as x goes to infinity of natural log of 1 plus 1 over x all over 1 over x. So reevaluating as x goes to infinity, this becomes 0 over 0. And I could use L'Hopital's. Okay, so what I'm going to do is, I noticed something about taking the derivative of this argument and the derivative of the denominator. Okay, so when I take the derivative of the natural log, it's going to be 1 over 1 plus 1 over x times the derivative with respect to x of the argument, which is 1 plus 1 over x. Okay? And instead of just writing down the derivative in the denominator, I'm going to write down the derivative with respect to x of 1 over x. And there's a reason why I'm doing this. What I want you to note is that the derivative of 1 plus 1 over x is actually equal to the derivative of 1 over x. Because remember, when we take the derivative of the constant 1, it's just 0. So if you notice that the derivative in the numerator and the denominator, they'll be the same, and they'll cancel, which is just a nice little shortcut. So I actually didn't have to compute the derivative in the numerator and the denominator. Okay, so this is going to be equal to the limit as x goes to infinity of 1 over 1 plus 1 over x. And as x goes to infinity, this is just 1. But remember, this is not the solution. We have to do step 2. We have to plug it in as the exponent on e. So putting this all together, we have the limit as x goes to infinity of 1 plus 1 over x to the power of x is equal to e to the 1, which is just e. Now at the bottom of the page, we have this definition about growth rates. Because you know, a lot of times when we've been evaluating these limits, we get infinity over infinity or negative infinity over infinity. And the limit actually depends on what grows faster, the numerator or the denominator. So if we're looking at the limit as x goes to infinity of two functions, f of x and g of x, and they're both equal to infinity, then if we take the limit of one over the other and the limit is 0, what that means is the function in the denominator is growing faster than the function in the numerator, because the denominator will get larger and larger and larger, and the numerator will not grow as fast, so the whole fraction will approach 0. Now if you take the limit as x goes to infinity and the limit is infinity, that just means the function in the top, in this case f of x, is growing faster than g of x. It could happen when you take the limit as x goes to infinity that you get some number m, where m is some positive number greater than 0. If that happens, then the functions grow at comparable rates. So on the next page, we'll look at an example 7, comparing the growth rates of these two functions, f of x, which is the natural log of x, and g of x, which is x cubed. So I'm going to go ahead and take the limit, and it doesn't really matter which one you put in the top and which one you put in the bottom. Okay. But I'll just go ahead and put f of x in the top. The limit as x goes to infinity of natural log of x over x cubed, well, that's just infinity over infinity, which is an indeterminate form. So I'm going to use L'Hopital's, and I get the limit as x goes to infinity of 1 over x over 3x squared, which is equal to the limit as x goes to infinity of 1 over 3x cubed. Okay, so as x goes to infinity, this is 0. So what does that mean? Well, what that means, so therefore, the bottom grows faster. Therefore, g grows faster than f. Okay, so that's what we can conclude. Now, if we were to graph this, again, I'm just going to do a quick sketch, nothing fancy. If f of x is the natural log of x, it looks like this. It's going to pass through the point 1, 0. And it grows, but slowly. Whereas our g of x is the cube function, passes through 0, goes up, and so on. So you can see that although they're both going to positive infinity, g's getting there faster. So what we can write, instead of writing all those words, g grows faster than f, well, f is the natural log function, and we're going to use the inequality less than. But it's really not true in all cases that f is less than g. So we're going to use these double inequalities. When you see the double inequalities, it just means that natural log of x is growing slower than x cubed. So this is another way that we can write it. Or you can write f of x grows slower than g of x. So that's going to bring us to this theorem 713, which is ranking the growth rates as x goes to infinity. So in general, our natural log functions tend to grow slower than power functions. Okay? And then those tend to grow slower than exponential functions, and those tend to grow slower than functions whose base is a function of x and whose exponent is a function of x. Okay, so that's it for 7.6.